Welcome back to Elements of Chemistry tutorials. Today we're going to talk about light. And light is really important in our discussion of electrons. So to get a good understanding of light, we have to look at who were the main players here. First of all, there was this guy Max Planck. He was a German physicist who around 1900 developed the quantum theory of radiation. He said that energy is not continuous, but emitted and absorbed in discrete, invisible packets of energy called quanta, and the energy of each quanta is directly proportional to its frequency. So we had the equation E equals hv, where h is Planck's constant, 6.626 times 10 to the negative 34 joule seconds, and v, or sometimes F, is frequency. He solved a problem that could not be explained by classical physics, and his equation matched experimental results, which is a really good sign that it works. And Max Planck laid the groundwork for others like Einstein, who used Planck's theories to help explain the photoelectric effect, which is what Einstein won his Nobel Prize for, not special relativity. Now, when we look at that unit of a joule is a very specialized unit. And when you think about a joule, it's important to note that a joule is a kilogram times a meter squared per second squared. So when we work with this, all of our wavelengths need to be in meters. So before we go on, we need to talk a little bit about just some parts of a wave. And we're going to do what's called a longitudinal wave. So here's what we call the normal. The normal is where the undisturbed material would be. I'm going to draw one wavelength. A wavelength is a complete wave from start to finish. The top of a wave is called a crest. The bottom of the wave is called a trough. And you can think of like an animal trough, a pig's trough, something like that. The height of a wave is called its amplitude. In light, amplitude would be a brightness. A bright light would have a high amplitude. A dim light would have a low amplitude. In sound, remember amp means loudness. But the important thing here is the wavelength, which we call lambda, that upside down y. And that's the distance for a complete wave. So this would be a complete wave. The other term we need is frequency. Now, frequency we often hear in the terms of hertz or megahertz. Frequency is the number of complete waves, so the number of waves per second. And quite often it's the frequency of the waves out in the ocean that make people seasick. Okay, so Max Planck was a really important guy in Germany. There's actually a huge science institute named the Planck Institute. Okay, so that was around 1900. 1911, we have Niels Bohr. He's a Danish physicist, and he developed the first quantum model. Remember, we had that planetary model? He was studying the light emitted from atoms, and he found that you could get light given off by certain atoms if you heated it or gave it electricity. And he looked at those colors of light and figured out that they were the electrons transitioning from orbital positions. He was also working in Rutherford's lab in Manchester when he determined these orbital distances of the electrons around the nucleus. So electrons gain energy and they jump to a higher orbital position by gaining that quanta, a discrete packet of energy. And an electron will release this quanta as it falls back to its original state, or it's what we call its ground state. And this released energy is what we see in a color of light. It's not always visible light. Our colors of light could be in the ultraviolet, the infrared, something like that. But remember, wavelength is important here. This other guy, de Broglie, he rationalized that Bohr's orbital distances had to be whole numbers of wavelengths moving around the nucleus. So a wavelength, 2 pi r n, where n is the energy level. Okay, so everything had to happen in full, complete waves. So when it went around the circle, and I can never draw this, if this was the nucleus, oopsie, we just lost our view here. Let me go back. It's where the crest and the trough will completely match back up. And let's see if I can, yeah, I kind of drew that. not exactly a scale, but you get the idea. And then the next orbital would be when you would have another complete set of waves going around the nucleus where they're not going to cancel each other out. So in whole numbers of wavelengths around the nucleus. This all led to the Schrodinger model of the atom. The Schrodinger model, if you've probably heard, is those fuzzy probability orbits of weird shapes. So there's some important equations we need to know. First of all, Einstein's E equals mc squared, where E is energy, m is mass, and c is the speed of light. That's a constant. Remember, we never use constants when we use significant figures. They're called exact numbers for a reason. Speed of a wave, or speed of light, is frequency times its wavelength. This is another one that we're going to use a lot. Energy is frequency times Planck's constant. We call that energy of a photon. And remember, we can use V or F for frequency. And Planck's constant, 6.626 times 10 to the negative 34 joule seconds. And this last one, energy of a photon, Planck's constant, speed of light over wavelength. Now, for those of you who are good at algebra, you've realized that we've taken our energy of a photon equation, solved it for frequency. If we take our energy, our C equals frequency times wavelength, C over wavelength equals frequency, and we've just substituted that in to the energy equation to get this equation right here. So let's try a few problems and see how we do. What is the wavelength? So we want to find lambda. So I'm going to mark lambda because I know that's what I'm looking for. Of a line in the hydrogen spectrum that has an energy. So my energy is 9.3, pen doesn't want to write here, 331 times 10 to the fourth joules. Well, I want to find wavelength. So I'm going to need an equation that has energy and wavelength in it. Well, this one right here looks like a good one. If energy equals Planck's constant times speed of light, both of those are constants from up here, divided by the wavelength, I can say that wavelength is equal to Planck's constant, speed of light, divided by energy. I've just rearranged that equation and came up with a new form. Planck's constant, 6.626 times 10 to the negative 34 joule seconds times my speed of light, 3.00 times 10 to the 8th meters per second. And I want to divide that by the energy, 9.331 times 10 to the fourth joules. Well, let's look at our math here. This joule is going to cancel that joule. This per second cancels out that second. We're left with units of meters, so that tells me we probably set this problem up right. So we're going to take 6.626 times 10 to the negative 34. I'm going to multiply it by the speed of light, 3.00 times 10 to the 8th. And I'm going to divide that answer by 9.331 times 10 to the fourth. And I'm going to get, let's look at sig figs. The only thing I can use for sig figs is my measured value, which is this energy. That has 4 significant figures, so my answer should have 4. 2.130 times 10 to the minus 30 meters. Let's try another problem. What is the energy of a photon of light that has a wavelength? Now I know my wavelength. Well, this wavelength's in nanometers, and I need to convert that to meters right off the bat. I know I'm going to use the energy equals Planck's constant, speed of light over wavelength. But I need that wavelength in meters so that things cancel out. So I'm going to take 635 nanometers for every 1 meter there's 1 times 10 to the 9th nanometers. You should have that from your metric system unit. Okay, so we're going to take 635, divide by 1. Oops, my calculator's messing me up here. Divide by 1 times 10 to the 9th. There we go. So that's going to give me 635, that's a decimal point here, times 10 to the minus 7 meters. 6.626 Planck's constant times 10 to the negative 34 joule seconds times 3.00 times 10 to the 8th meters per second divided by 6.35 times 10 to the minus 7 meters. We're going to do some canceling out here. Seconds are going to cancel seconds. Meters cancels meters. I'm going to take Planck's constant, 6.626 times 10 to the negative 34 times 3.00 times 10 to the 8th. I'm going to divide that by 6.35 times 10 to the minus 7. I have 3 significant figures in that number, so I only need 3 in my answer. So I'm going to get 3.13 times 10 to the minus 19, and the only unit I have left is joules. Find the frequency of light with an energy. Okay, so we have an energy. So if my energy is 2.179 times 10 to the minus 18 joules, and I want to find frequency. Well, if we go to our energy equations, energy is frequency times Planck's constant. So if energy is frequency times Planck's constant, I can take my energy divided by Planck's constant, and that's going to give me my frequency. So I'm going to take my energy, 2.17 times 10 to the minus 18 joules. I'm going to divide that by Planck's constant, 6.626 times 10 to the negative 34 joule seconds. .17. My calculator just went to sleep. 2.17 times 10 to the negative 18. Make sure when you do your negative, you're using that change sign button, not the subtract button. I've answered a few questions for people and they're just putting the subtraction sign instead of the change sign button in. Divide by 6.626 times 10 to the negative 34. I'm going to change sign button again. And this is going to give me, I need 4 significant figures. 3.275 times 10 to the 15. And this joule is going to cancel this joules. So we're going to get 1 over seconds, which is the same thing as a hertz for our frequency unit. Okay, number 4. We have a hydrogen lamp that emits several lines in the visible spectrum. One of these lines, so we have a wavelength. So we're going to go ahead and convert that wavelength because we know we're going to need it in meters. So 410 nanometers for every 1 meter. There's 1 times 10 to the 9th nanometers. So that's going to give me 4.10 times 10 to the minus 7. Now 410, let's look at this one carefully. That 0 is not significant. So we really don't need that 0 right there to make sure we have our significant figures straight. So that's my wavelength. What color is associated with that wavelength? Well, to do that, you're going to have to go to a spectral chart. On a spectral chart, you'll look it up and just see what the color is. I believe 410 is like in the orange range. What energy is associated with that? So this one here, you look up. Just look at the visible spectrum. What energy? Well, if energy It's Planck's constant speed of light over wavelength. We're going to have our 6.626 times 10 to the negative 34 joule seconds times 3.00 times 10 to the 8th meters per second. We're dividing that by our wavelength, 4.101. Oop, don't put that 0 in. I almost did. Times 10 to the minus 7 meters. So Planck's constant times speed of light, divide by 4.1 times 10 to the minus 7. And we want two significant figures, so that's going to be 4.8 times 10 to the minus 19 joules of energy. We need to find its frequency. Well, we can leave frequency a couple ways. Speed of light is frequency divided by wavelength. Let's do it that way this time. So speed of light, 3.00 times 10 to the 8th meters per second. We're going to divide that by our wavelength, which was 4.1 times 10 to the minus 7 meters. This is going to give me 1 over seconds, which is the same thing as a hertz. I got a calculator here, and I want two significant figures, 7.3 times 10 to the minus, no, positive 14, 10 to the 14. So not a negative sign there. Maybe I can erase it. Okay, good. Okay, so your turn. Let's go ahead and take a few moments and try these problems and we'll see how you do. Remember, as always, go ahead and stop your video and then come back to it. Okay, it looks like we're back. So let's look at this one. A mercury vapor lamp emits a light with a wavelength of 4.45 times 10 to the minus 7 meters. Find the energy. Well, this is going to be the same equation we've been doing here. E equals hc over lambda. We've got the wavelength already in meters, so we're just going to do the 6.626 times 10 to the negative 34 joule seconds times our speed of light, 3.00 times 10 to the 8th meters per second. And we're going to divide that by our wavelength, 4.45 times 10 to the minus 7 meters. We have three significant figures, so we want to have 3 in our answer. So we go ahead and take run the calculator. Some of you may see the advantage of going ahead and doing this multiplication of H and C, Planck's constant and speed of light, and just holding that in your calculator. We're going to divide that by 4.45, second e to the negative 7. Sorry, I talked myself through it. We want three significant figures, so this is going to be 4.47 times 10 to the minus 19 joules for our energy. A photon of light carries an energy of 3.55 times 10 to the minus 20. Sorry, I should put the unit joule in there. Would have the frequency of what would be its wavelength of the photon. Well, if we know its energy, we can go back to our equations. We know our energy. Energy is Planck's constant times frequency. And we know its energy. If energy is Planck's constant times frequency, I'm going to use the V here, That means that frequency is energy divided by Planck's constant gives me my frequency. So 6.626 times 10 to the negative 34 joule seconds divided, sorry, I did that backwards. Got to put our energy on top. 3.55 times 10 to the minus 20 joules. So 20 joules. Now divided by our Planck's constant, 6.626 times 10 to the negative 34 joule seconds. That's going to give me my frequency. And I want 3 significant figures because of that given. My frequency is going to be 5.36 times 10 to the 13, 1 over seconds or hertz. We want to get the wavelength. So we go back to our equations and look at wavelength. Speed of light divided by frequency gives me my wavelength. So now I'm going to take my speed of light, change my colors here so you can see this one a little better. I'm going to take my 3.00 times 10 to the 8th meters per second. I'm going to divide it by that frequency, 5.36 times 10 to the 13, 1 over seconds. And that's going to give me an answer in meters, which is going to be my wavelength. And that's going to give me a wavelength. And I want to still keep 3 significant figures. So 5.60 times 10 to the minus 6 meters. Okay, a photon of light, we have a wavelength. If our wavelength is 525 nanometers, by now you probably realized the trick. It's going to be 5.25 times 10 to the minus 7 meters from a heated element. What is the energy of the photon? Well, and we need the frequency of the light. Let's go ahead and do frequency of the light. No, let's just do energy. So if energy is Planck's constant times speed of light over wavelength, divide by that wavelength, and we want this answer to have 3 significant figures. This is going to come out with an energy of 3.79 times 10 to the minus 19 joules. Okay, so there's one of our answers. If energy divided by Planck's constant gives me my frequency, I'm going to take 3.79 times 10 to the minus 19 joules divided by my Planck's constant, 6, pen doesn't want to write, 0.626 times 10 to the negative 34 joule seconds. This is going to give me a frequency unit to 3 significant figures of 5.71 times 10 to the 14th hertz. Okay, I hope this helped you with a bit of light equations. The whole part about color and spectrum, you just got to look up a color spectrum and see what wavelengths are at what colors. And I hope this helped. As always, be kind, stay safe, and have a wonderful tomorrow. Have a great day, everyone.